this video, we'll be looking at the big physics idea of physical quantities and units. So we quantify things in physics. It helps us make better sense of the universe if we can actually quantify, take measurements, and then apply mathematical thinking to the universe. So all physical quantities will have magnitude, sort of tells us how much, and we'll also have a unit, sort of an agreed upon way in which we standardize and we measure things. Some quantities will also have a direction associated with it. Certain quantities, it's important to sort of make sense of what direction they're pointed in. And we call those quantities that have magnitude and direction vector quantities. Let's look at some examples of scalar quantities and vector quantities in the branch of physics known as mechanics. I'll put vector quantities in violet. So one of the first vector quantities that we learn about is called displacement, which is just a change in position. So going from, say, this point all the way over to here, that would be a displacement. We like to use the letter S for displacement in ACE physics. It comes from the Latin word spatium. The rate of change of displacement gives us velocity. And so that's like taking displacement divided by time. And that's also a vector quantity, velocity. So velocity is equal to displacement divided by time. Okay? The rate of change of displacement is velocity. The rate of change of velocity is acceleration, another vector quantity. And so that's sort of the change in velocity over the change in time. Acceleration is related to yet another vector quantity, force, by arguably the most famous and, well, perhaps not the most famous, but arguably the most important equation, at least in this level of physics, Newton's second law, which says that force equals mass times acceleration. Now, I was too quick to write that M with violet vector. Mass is a scalar quantity, and so I'm going to put scalars in tasteful scarlet. All right, and hopefully you can see that that's a scarlet scalar quantity, right, with my scarlet crayon. One of the ways that velocity is connected to another vector quantity is through the idea of momentum, which is another vector quantity. So momentum P is equal to, and I'll be careful this time, the product of mass and velocity. So I said it's connected to velocity via that regard. This concept map that I'm building here is useful to see how these various vector and scalar quantities are connected in mechanics. Sometimes we're given questions where we may know something about velocity, but we're asked to solve for force, or we're told something about momentum, but we need to solve for force. It's not immediately obvious here, but momentum and force are actually very fundamentally connected. Force is indeed the rate of change of momentum. And that's the definition of force. Force equals the change in momentum over the change in time. That becomes F equals ma when mass is constant. Another way that force is connected to momentum is through this idea of impulse, another vector quantity. Impulse is force times the change in time. Impulse and momentum are connected via a very fundamental way known as impulse-momentum theorem, which says that the change in momentum is equal to the impulse. Which you can just see as a rewritten equation here with the definition of force. Multiplying both sides by delta t, we see impulse equals the change in momentum. So things change their momentum when impulse is delivered. Let's talk about a few more scalar quantities. So velocity the vector is connected to the vector momentum via the equation momentum equals mass times velocity. but velocity is connected to a scalar quantity, kinetic energy, via this equation. So kinetic energy is a scalar. It is the energy of motion. And it's equal to 1/2 mass times velocity squared. Force is related to a scalar quantity, work. Work equals force times displacement. And really this is the dot product, and so we can multiply two vectors and get a scalar because we're really taking the dot product or the scalar product of these two vector quantities. Only the component of force that acts in the direction of displacement contributes to work. So if both of these vectors are pointing in the same direction, we don't need to sort of worry about that because the cosine of 0 is 1. But the full form of this equation is work equals force times displacement times the cosine of the angle between these two vectors, the sort of smallest angle between these two vectors. And if indeed the two vectors are pointing in the same direction, then the angle between them is 0, the cosine of 0 is 1, and so that just sort of vaporizes out of the equation. Power is yet another scalar quantity. And power is equal to the rate at which work is done. So work divided by time. And so you can see how work is connected to power. There's lots of rates of change here. The rate of change of displacement is velocity. The rate of change of velocity is acceleration. The rate of change of momentum is force. The rate of change of work is power. And there's another important theorem in physics called the work-kinetic energy theorem, which says that the work done to an object is equal to the change in its kinetic energy. So work is equal to the change in kinetic energy, showing how work and kinetic energy are related. There's a lot of different physical quantities here on this concept map, and these are a lot of the most important ones that we study in mechanics, but there's not all of them. For example, we could talk about how changes in position in a gravity field would give us gravitational potential energy, which is another type of energy, which we could then convert into kinetic energy. There are different types of potential energy. I just mentioned gravitational potential energy, but we could also think about the potential energy, say, stored in a spring. Elastic potential energy could be stored in a rubber band, for example. And so energy exists in many forms, but we should be familiar with some of the fundamental conservation laws, like energy is neither created nor destroyed. Another fundamental conservation law in physics deals with momentum. Momentum is conserved, another quantity that's conserved. Angular momentum sort of finishes out the three great conservation laws in physics. Angular momentum is another quantity which is also conserved. We'll study each of those topics in a lot more detail in subsequent videos. In a previous video, we looked at a concept map that connects a lot of the ideas contained in the physics of mechanics. I'd like to go back over that concept map and write down the SI units that we measure each of these quantities in. Displacement is measured in meters. Velocity, being the rate of change of displacement, is measured in meters per second. Acceleration, being the rate of change of velocity, is measured in meters per second, or meters per second squared. Meters per second squared is another way to sort of write the units of acceleration. Force has the SI unit of a Newton. And a really important idea in physics is to make sure that we have units which agree on both sides of the equation. We want to have homogeneity in our equation. And so a Newton of force is really a kilogram of mass times a meter per second squared of acceleration. Another way to show this per second squared is with a negative index, like I've written over here. So this is a really key idea, that we have many derived units in physics that come from just a few base units, and we'll talk about base units also in a subsequent video. The unit of energy is the joule. The unit of power is the watt. And so if power is work divided by time, then we could think about 1 watt of power as being equal to 1 joule of work per second of time. So 1 joule per second is a watt. 1 joule per second is a watt because a joule is the unit of work or energy, work and energy being the same thing via this work kinetic energy theorem. So a joule per second is a watt of power. I already mentioned that the units of work are the same as the units of energy, joules. And so another thing that we could realize is that a joule of energy or work is equal to a newton of force times a meter of displacement. So 1 newton meter is equal to a joule. Now, momentum and impulse don't really get their own sort of unique units. They're just sort of whatever units we get from this equation. And so the units of momentum are kilogram meters per second, because momentum is the product of mass measured in kilograms times velocity measured in meters per second. So the units of momentum are just kilogram meters per second. Another way to think about that sort of change in momentum, so a change in momentum would also have these units, is that it's equal to a newton of force times a second of time. So a newton second is the same thing as a kilogram meter per second. And we could show that if we were to substitute in a kilogram meter per second squared for a newton here, one of the seconds would cancel and we'd have this. I think that concludes all the units contained on this concept map.